So nanoscale electrochemistry, it really kind of means two things. One is just the idea of getting things down to the nanometer scale, but the bigger implication of it is when the properties of the system change. And so when you get to scales that are really small, things behave differently. Nanoscale is the next revolution in electrochemistry as we went to even these smaller scales where we have new kinds of phenomenon related to the dimensions, and also, everything happens a lot faster when it's happening at these really small scales. Biology actually operates at the nanoscale inherently. And so now you're really talking about being at the scale of molecules of proteins. And that gives you an opportunity to think about new ways to measure maybe one protein at a time, or understand how one protein interacts with one other protein. If you start thinking about trying to measure one of something, does measuring one thing actually reflect what the entire sample or the entire group of molecules that you're measuring is trying to tell you? And so really a lot of things, especially when you're talking about nanoscale electrochemistry and biology, is getting at a combination of statistics and the nanoscale electrochemical measurements. In synthetic systems, we like to make nanopores out of lots of different kinds of materials. They can be things like carbon nanotubes or polymer membranes, or my research group uses nanoscale pipettes to do a lot of our research. In electrochemistry, what nanopores give us is a way to control electric fields and concentrations of ions and molecules in a very small, well-defined space. And a nanopore really presents kind of a different kind of electrode than what you would typically use. With a nanopore, we're usually looking at how ion transport through that pore becomes occluded or becomes enhanced based on the sample and the properties of what you're trying to measure. So my group has spent the better part of 15 years developing a tool called scanning ion conductance microscopy, or SICM, which lets us measure the local ionic conductance at interfaces. SICM is great for taking just topographical images, but what we've spent a lot of time trying to do is incorporate chemical selectivity of some kind into the measurement that we're making. So to do that, we modify the probes to impart special characteristics. For instance, recently we've done things like added ion channels to nanoscale pipettes. And what that does is it essentially lets the protein channel become a sensor. If we move that nanoscale pipette that's modified with the protein channel then near an interface that we're interested in, we can measure what molecules that channel responds to selectively. I really believe strongly in the idea of building new instruments that maybe we don't even know exactly what we're going to do with them initially when we build them. We're just trying to push the limits of what we can measure in terms of measuring something faster or lower concentrations or in a noisier environment. And then once we have that tool, we're going to see where we can apply this tool in the physical world and what kinds of new measurements that we can make that'll let us understand how the world works in a better way. So a year ago when the pandemic started, we were disappointed, but it doesn't really change our need for stimulation and the need to talk to other people about our science and about their science and try to see where there are commonalities and things that we can learn from each other. Pittcon has a special place in the analytical chemistry community, and I think a lot of us in sort of my generation had a lot of our sort of formative or pivotal experiences in analytical chemistry at the Pittsburgh conference.